Good morning and welcome back to our live coverage of a special event in space science, a milestone in the Rosetta mission. Today is the day when the Rosetta spacecraft will launch its lander Philae to land on the comet Churyumov-Gerasimenko. I'm Monica Jones and I'm reporting here live from the European Space Agency in Darmstadt. Now, we've already passed all four crucial go decisions since yesterday evening. So at this point we are into the touchdown procedures. At 7:30 this morning, Rosetta also completed its complex trajectory maneuver, which was putting it into a more direct angle towards the comet. And as I mentioned, we already have the fourth go. So we're well underway. Let's quickly take a look at what exactly has been happening since it all started last night. A short while ago, we passed the first hurdle. We got the first go ahead with the landing sequence.
The spacecraft is very healthy, and we have had just right now a go from the flight control team and from flight dynamics. Great news, we are go from the lander. It's 3:30 local Darmstadt time. We needed a bit more time to do all the final checks, but everything's okay. The commands have already been sent to give the go on board, and so the next big steps now is the maneuver, which will start around 7:30 local Darmstadt time here, and then the final go no-go an hour later.
Actually, this night was quite busy for us here in the control room, also for the team in the lander control center in DLR. So we had to repeat some activities there, and we indeed do have a problem with the cold gas system aboard the lander. But everything else is nominal now, and we are on go, and indeed separation will take place in about 2.5 hours from now.
We switch on our first instrument, ROMAP. Since a couple of hours, is already collecting data on the magnetic field of the comet, and soon, in something like half an hour, we have to switch on other instruments like MUPUS and SESAME, instruments to characterize the properties of the cometary surface and subsurface.
Great news from the main control room. Flight dynamics told us the maneuver performed very well. We're go for lander delivery. So we've also just sent the commands, and they're on their way to the spacecraft. The spacecraft is now slewing to the separation altitude, so we have LOS. We've lost telemetry, which is fully nominal, and now we just have to wait for separation.
So that was a quick wrap-up. You see that quite a lot of people are quite busy. Sylvain Lodiot just now giving us the last go straight from the main control room here at the European Space Agency. We also had a comment there from LCC in Cologne, and of course Stefan Uller-Metz, who is responsible to a large part for the lander. And you also heard that there were some complications during the night, so certainly quite exciting. But right now we are at a point where there is no going back, because now all the procedures are automated. The procedures that will carry the satellite into the next sequence. We will see the most crucial one, namely the separation, in about half an hour from now, and we will obviously be here to cover this for you and also give you a bit of background information in case you were wondering why in this wrap-up I'm wearing a different jacket. Well, that was of course last night. So here we are, and a lot of people are watching. The room here is also getting fuller. We have a lot of media vans on the compounds here at ESA. And I also know that there is a lot of traffic on Twitter. And just in case you would like to send a comment or a question in, our hashtag is Comet Landing. Maybe this would be a good point to quickly have a look at what kind of tweets we have so far. Let me see where I find them. If we get any in, if not, then we would like to cross to the main control room. Okay, I can't see the tweets. Yes, I can't. Here we are with the tweets. All right, what do we have? Let's just pick some. Really hope everyone teaching physics today will be talking about Rosetta. Yes, we hope so too. I'm running out of words to describe just how incredible the Rosetta mission is. We're rewriting textbooks tonight or today, depending from where you're watching us right now. Did Life on Earth begin with the help of comet seeding? We may be able to find out with Rosetta. And all being well today should be a great day for science, humankind, and our knowledge of the universe. Good luck. Love it when a space story leads the news. We all love that, and let's hope that the news is going to be good news. And we're ready now to cross over to the main control room. The world is watching, and of course the people inside the main control room here at the European Space Operations Center are watching too. In particular, this gentleman here, Paolo Ferri, head of ESA's operations department. Paolo, the separation of the lander is actually happening right now on board the orbiter, but we won't know until about half an hour from now due to a time delay. Can you explain that to us?
Yes, Monica, the separation happened, in fact, 2.5 minutes ago, or at least we hope it happened. There were some final checks on board to be done automatically, and we hope that they were all successful. The distance is so large, 500 million kilometers, that the signal at speed of light will take almost half an hour to reach us. So we will be able to confirm it in about 25 minutes from now.
Okay, well, we'll all look forward to that, and we hope that you can confirm it then. That would be fantastic news, Paolo. Take a deep breath. We'll be talking to you later again. Thank you for now. So it's clear, distance and time for us sometimes very difficult to understand, but nobody ever really worries about the fact that it actually takes the sunlight 8 minutes to travel from the sun to Earth. So now you can imagine how far away Rosetta is at this moment, when it takes 28 minutes for the signal to reach Earth again. But what exactly is Rosetta doing out there? Well, let's take a look at that.
The Rosetta orbiter has been orbiting the comet for 3 months. During this time, it has observed and mapped the comet at distances ranging from 7 to 20 kilometers above the surface. This information is crucial for operational maneuvers and preparing for the landing. This boulder, named Cheops after one of Egypt's Great Pyramids, was 40 kilometers across. Detecting boulders like this helped eliminate potential landing sites. The comet's temperature measured by the Virtus instrument is -70 degrees, warmer than expected. This led scientists to conclude the surface was covered in dust and little ice. It also detected water and carbon dioxide in the region above the comet's neck, and will map the different gases coming from the comet and how these change with its activity. Measurements have also been made of the comet's elevation and gravity. The Miro instrument took the comet's temperature below the surface, while Rosina measured the comet's density and detected a distinctly odorous combination of gases, including ammonia, methane and hydrogen sulfide in the comet's atmosphere or coma. Both Miro and Rosina have also detected water and carbon dioxide. Detecting these two gases helps build up an idea of the structure of the comet's ice. Ion beam analysis of one of Cosima's first dust grains, nicknamed Boris, has produced its first results. It detected magnesium, which was expected, and also sodium, which is of much more interest. There was even time for a selfie, and ground-based observation from the Very Large Telescope has shown the comet's coma stretching for 19,000 kilometers. More orbiter science results will be published in scientific journals, and the lander instruments will also provide further data during Philae's descent and from the surface. Rosetta science will continue for more than a year, watching the comet evolve as it makes its closest approach to the Sun.
Yeah, we're not quite yet at this point when the lander is approaching the comet that close. That'll be hopefully later this afternoon. Let's talk a bit more about the science. And here with me is Matt Taylor. He's the Rosetta project scientist at the European Space Agency. Matt, we've just heard in this video quite a lot about all the science that's going on, all the data we will get, and all this is very well. But let's just strip it down to the very fundamental question. Why is Rosetta there?
That's a good question. I've said it before, Rosetta's the sexiest mission that's ever been. She is sexy, but I never said she was easy. And we've seen that overnight. It's there to fully characterize a comet. These comets are time capsules from the early solar system. So by examining those, we get a feel for what the situation was then and how we've evolved to the situation we have now. With the Rosetta orbiter, we started science operations earlier this year. We will characterize globally the comet. But the lander today, once it gets down on the surface, will give us the eye in situ. It's really going to give that scratch and sniff. So we really get the ground truth.
So when we just look at the moment, where are we now? In this right moment, before separation or before having the signal that separation happened, what does this mean right now?
Well, we've done rendezvous. We're at the cusp of ticking off the final operational aspect of the mission for me personally. So we did the rendezvous in summer. We started escorting the Comet. These have never been done before. And now this is the final tick box to say, right, now we're going to deploy the lander. So we're on the edge now. This is our longest day, and it's going to be a good one.
Okay, well, we know that Philae has been basically just traveling for 10 years, not doing much. Once it's down there, will it immediately start working?
Well, it starts now. We've heard earlier on from some of our colleagues at LCC, the instruments are coming on as we go through descent. That's part of the science of the mission. We have a descent phase where we'll be taking measurements of the magnetic field and the local environment, as well as monitoring using the CONSET experiment, the signal between the lander and the spacecraft to get an idea of what that descent trajectory is like. And then as soon as it touches down, we'll be doing science. So yeah, it's designed to do that in the most efficient way, and we've got it all to wait for now. It's very exciting.
It's very exciting. I can tell. Matt Taylor, project scientist of Rosetta, thank you very much.
Thank you.
I will need your microphone, and I look forward to speaking to you again. Cheers. Now, let's talk a bit more in detail about science with three scientists, of course, who have joined us now. Starting with the lady here, Claudia Alexander, the project scientist for the US Rosetta participation from the Jet Propulsion Laboratory in Pasadena in the United States. Good to have you here. To my right here is Holger Sirks from the Max Planck Institute in Göttingen in Germany. He is the OSIRIS principal investigator. And right in the middle is Mark Bentley, PI of the MIDAS experiment from the Institute für Weltraumforschung in Graz, that is in Austria. So it's brilliant to have you here. You've already got a microphone, so, and we're matching as well. Brilliant. We haven't spoken about that before, though. Holger, let me start with you, because we also already spoke during the wake-up and during the rendezvous, and of course there's been a long journey. And I should imagine that you must have been really surprised when, in early August, we saw those first pictures. And we always thought it would look, that the Comet 67P would look like some duck or some weirdly shaped potato, and then suddenly the first picture came, and it was this.
Well, this was a big surprise to us. So we expected a somewhat irregular shape for this comet from the little wiggles in the light curve seen in by ground observation over the rotation of the body, but not such a structure. So it looks bilobal, so like two bodies merged in space a long time ago at walking speed, so low velocity, or just one big monolith that eroded by the eons into this wonderful shape. Even the building blocks for this nucleus could be part of a larger piece from the early days of the solar system. So it's very interesting, and it will take us all the instruments on board spacecraft and the lander, to understand this nucleus and the formation at the very end.
I mean, certainly as we got closer and closer, and then of course with this high resolution, the images, the quality of these images, and to see a body that is that old and so far away is amazing. But what is the scientific background of OSIRIS and the pictures it takes?
Well, we want to understand cometary activity. That's why we are there. So we have unprecedented details now, so down to 10, 15 centimeter pixel resolution, never seen, never before by the flybys or for the other missions. So we see activity now sourced in a certain region, and don't understand it. So we want to make sense of it by getting all instruments together, understand the thermal situation there, understand the material strength, porosity, so how sublimations, the escape of water and the supervolatiles can occur, and then we'll get a better grip on how comets, this comet and the larger population of comets really work.
Yeah, so OSIRIS is a very important instrument and hopefully will provide many, many more pictures. Mark, MIDAS, also a very important instrument. It's a kind of microscope, if I understand correctly, on the orbiter that analyzes small dust particles. How does that work?
So MIDAS exactly is really interested in the very smallest particles. So we're talking here really small. A human hair is already too big for us to analyze with our microscope. We're looking at particles that are micron sized, so a millionth of a meter in size, a thousandth of a millimeter. And these are really what we hope are the building blocks, not just of Comet, but also perhaps the solar system itself. So that's what we're looking for. And we do this by basically putting out a sticky target, holding it up to the comet, and waiting until the dust is collected, and we've exposed so far for several weeks. That's the easy bit. Of course, the hard bit is then finding these particles that are so small in order to analyze them, and that is still ongoing.
But of course, MIDAS isn't the only dust analyzing instrument on board. There's also GAIDA and COSIMA. So in what way does MIDAS differ from them?
Well, of course, to understand the whole story, as Holger says, every instrument has to contribute. We have to work together. So COSIMA will analyze, as we've seen there, the composition of individual grains, and GIADA gives statistical information and also measures individual grain mass, size, velocity. But it's only MIDAS, or MIDAS as you say, that can really look at these tiny grains, and we do this, we're using an atomic force microscope. So these are too small to see with light. So we have to use a really sharp tip mounted on a cantilever, so a kind of springboard, and we tap the samples very gently, and we do this over the whole surface, and we build up this three-dimensional picture of the valleys and the peaks of particles around the size of a red blood cell. Yeah. So that's the hope. Of course, we still have to find one yet.
But I'm just trying to imagine to pat these dust particles very gently 500 million kilometers away. Claudia, the United States have also contributed to the Rosetta mission, of course, with 3 instruments, the plasma instruments IAS, the UV instrument ALICE, and the microwave instrument MIRO. Why? What's the reason for NASA to provide these instruments?
Well, we put out a call, and these were the instruments that responded in the best way to the call. And by the way, it's the IES, the ion and electron sensor.
Okay.
The E is for electrons. Yes, I mean, a plasma instrument is essential if you're trying to understand the plasma environment. So this is a key instrument in that kind of consortium of magnetic fields and particles suite of instruments. So that's a key instrument there. The ALICE instrument, this is the first time we're flying an ultraviolet instrument to study a comet. So that was a unique contribution that the ALICE instrument was able to make. And MIRO is another first-time instrument. The first-time microwave instrument has been miniaturized so that it can be flown for planetary science. And so these are 2 first-time experiments that we're flying in this environment.
Would you say that the cooperation between European Space Agency and NASA is a fruitful one from your experience?
I think it's a beautiful one. It's a pleasure to be able to cooperate and to be a partner in this kind of international cooperation, and we want to be a good partner. We take pride in really trying to be the best partner we can be from JPL, and it's been this is an enormous payload, so it's a large consortium of scientists, and so to be able to make a contribution here is a pleasure.
It's great. Well, we are coming closer to the moment of separation, which is why I would like to go straight to Holger again. So far, OSIRIS was mostly involved in trying to find the perfect landing site, and we hope we did find it. We've got some images where we see how it got closer and closer and what Philae's new home might look like in a few hours from now. But we do expect to see more pictures, obviously, from OSIRIS later from the landing site, taken from right there. When about do you think we can expect these pictures to come in?
Well, we take a number of images and we take rasters, so wide field and image, and then a 2x2 raster with a high resolution camera. So a set of 5 images every hour. So from the earliest possibility when the orbiter has turned around to get the lander into the field of view, to the last moment when we touch ground and verify landing. So the earliest possibility to see the lander would be with the first, if we caught it with the first image, something like 2 o'clock in this afternoon. So if it happened to be in the last image, and we don't know, it will be around 3:30 this afternoon.
Okay.
And we are looking forward to see the lander in front of deep sky in good resolution.
Yeah, we're absolutely looking forward to it. Holger, Mark, Claudia, thank you so much for telling us a bit about your instruments, and best of luck. Hopefully the journey continues, because we are approaching bit by bit the actual separation, and there are a lot of requirements, of course, and a lot of different teams from various parts here in Europe and around the world were included and involved in the Rosetta mission. We're heading over now to the Space Operations Navigation Center of the French Space Agency in Toulouse, where we see Jean-Paul Berthia at SONC, hopefully. There we see the main control room already. And Jean-Paul is standing by here, Systems Engineering and Flight Dynamics Manager. Do tell us, what's been SONC's job in selecting the landing site? We already know that Osiris, the camera, provided the pictures. What did SONC do?
Well, actually, SONC with the architecture, many people were involved in the site selection process, because that's very important to select the both sites for the landing. Actually, the scientists are the prime actors in this discussion. The scientists want to select the best site for science, but then we have to play with constraints. Some of the constraints are mechanical. The lander was designed only to withstand a certain impact upon landing, and then the slope, where the ground where the lander lands, is limited. If the slope is too high, the lander will tip over. And then there is the fact that you have to be able to deliver the lander to where you want it to go, and that's the work of the flight dynamics engineers at ESOC. And SONC basically was the in-between actor who tried to get all these people together to discuss and to help them select the best site by providing information in a way that could be understood by the scientist, and in the end providing the pre-selection of the sites.
Okay, Jean-Paul Berthia from Toulouse, SONC, thank you very much for this now. I'm sure we'll be catching up with you again, but I hear that we are really getting very close to separation, and we still have to check with the Lander Operations Center in Cologne. So thank you very much for this now, and we go straight over to Koen Kurtz at the Lander Operations Center in Cologne. I believe we're there right now and see the main control room there. Koen should be visible any moment, and here he is, standing outside the main control room. So you're the lander technical manager at DLR, and you performed a number of tests and simulations with the lander to be sure that the landing will actually work in the moment of touchdown. What exactly have you done?
That's correct. We've been conducting many tests over the last 3 years, in particular during the Rosetta hibernation phase, in order to prepare not only for the separation, descent and landing that we're conducting today, but also for the associated science phase that we conduct immediately starting from touchdown, which will last about 48 hours, and afterwards we'll have hopefully a very long-term science phase that we've prepared as well.
Well, it sounds like everything is going to work, though we heard earlier that there were some complicated moments. You confident that we'll go ahead with it all?
Yeah, of course, I'm very confident. We had some hiccups last night. It was a very short night for myself, but this is what we've been training for all these years. We've prepared contingency procedures. For example, when we saw that the ADS tank opening did not succeed, we already had contingency procedures prepared, agreed with our colleagues at ARMOC, so we could rerun them in a short time. This is exactly the things that we have been training for all these years.
Okay, well, Koen Kurtz, best of luck. Obviously, we'll all cross our fingers for you. Thank you very much for now. That was Koen Kurtz live from the LCC in Cologne. We have a couple of minutes left, and here with me is Mark McCaughrean, the European Space Agency Senior Science Advisor to the Director of Science. Now, Mark, we already spoke about that Rosetta is really a very ambitious science project, but European Space Agency has more to offer. So perhaps right now, just take a moment to give us some more key projects.
Absolutely. You know, we're going out here to look at this particular object, this comet, because that's one of the key treasure chests of information about the birth of the solar system. But we have the solar system, it's there. We have Venus. We have a spacecraft there, Venus Express. We're at Mars with Mars Express. We're going back to Jupiter. We're at Saturn. And we have missions going back to Mars. So we're trying to piece together this whole puzzle about how this solar system that we're part of, that we live in, how it was put together, and of course, to go beyond that and to try to understand how planetary systems around other stars are. Because one of the big key questions that we're all fascinated by, are there planets elsewhere, but is there life on those planets? Can we find evidence for that? So trying to understand the solar system we live in is kind of a ground truth. We know what this one is like if we study it in detail, but how does that extrapolate out into the rest of the universe? So our astronomy missions then look for planets around other stars. We have several of those, and try to understand the bigger universe as well.
Now, Rosetta took 20 to 30 years to become reality. What will be reality in 20 years from now?
Well, you know, because it takes so long, those sorts of missions are being planned now. They've been selected. We have missions already in the pipeline out to 2034, that 20-year timescale. So as I said, we're going back to Jupiter, in particular to investigate the icy moons of Jupiter, where we know there's a thick ice crust on these moons, but beneath that are deep oceans full of water. Now, we won't penetrate into those oceans yet with these missions, but we can investigate from outside how that might be in terms of habitability potentially. But we also do insane things. We have a mission way out there, which we'll launch around 2034, which is going to look for tiny ripples in space-time, gravitational waves propagating from merging black holes. This is a signal we've never seen. It's a carrier of unique information. But with our big mission, which we're going to launch on that timescale, we can investigate the whole universe, in a sense, with one telescope.
So ESA, whatever happens today, continues to write history in years to come. Mark McCaughrean, thank you very much for now. I'm hearing that we are really only moments away, hopefully, from one of the crucial moments of this morning, the separation of the Philae Landing from the orbiter Rosetta. You are watching a live coverage of the hopefully successful landing, the first ever landing of a man-made probe on a comet Churyumov-Gerasimenko. And now would be a good time for us to cross over to the main control room at the European Space Operations Center to watch as things unfold.
And power that minus 1 minute 15 seconds instead of minus 5 seconds.
There seems to be a disturbance with the spacecraft.
Okay. Race stable? No. Not yet. They're coming back. For the all stations on my loop report separation.
It was nice meeting you. You'll find another reason.
Taxi, besagte Taxi. Der ist Aufführung. Well done, guys. Yeah, the procedure could be improved, yeah?
Next separation.
Again?
Next separation.
Next time.
Anybody tell me if they are talking to me? Because I don't hear anything. The audio is gone.
I have kind of audio. That's okay.
Okay, Andrea, I'll keep asking. We want to hear it from your lips. We have the signal. The separation worked out. It functioned.
Definitely. We've been living and flying together for 10 years now. Philae has gone. It's on his path down to the Comet. Definitely. We see it in telemetry.
Fantastic, Andrea. Congratulations.
Yeah, thanks a lot. It goes to the large team that we are here at this. We spent the night trying to recover the lander completely, and this was successful. We are all glad that it worked flawlessly in the last minutes.
Yeah. Well, we're all nervous. We all have sweaty hands, Andrea. I know that there's still many more crucial moments. The most crucial one in a few hours from now, the actual landing, but we've taken the first hurdle. I was wondering what happened to Stefan Ulamet, the Philae Lander manager, who obviously was very nervous, and he's next to you.
He's next to me. Now it's up to me to go down. We've done our job. Stefan, it's yours.
But he cannot hear me, can he?
Yes, I can. In the meantime, I can hear you again. Yep.
You can hear me. Fantastic.
Yes. Yeah.
So, after so many years, and especially after such a stressful night, how do you feel right now?
Well, released or relieved. So we were together for 10 years. It's time to separate, and we successfully separated now. So the lander is alone. It's on its own now. It's due to gravity to bring it down in about 7 hours from now, or 6.5 on ground for the landing.
Okay, well, and we'll be, of course, there, and you'll keep an eye on the telemetry, the data that tells you about everything that happens in the meantime. Just briefly, what's happening in the next few hours before we will catch up with you?
Yeah, so in about 2 hours we should get radio link from the lander while it's still descending. So we will get first data, housekeeping, but also some science data. Soon also maybe this farewell image of the orbiter. So part of this can be transmitted already during descent. But then, of course, at touchdown itself, we should see the touchdown signal, the harpoon firing signal, and then the real science will start on the surface.
Okay, Stefan Ulamet, I let you take a deep breath now, relax a bit before the next bit of work. Thank you very much, and congratulations for getting this far. And I believe we also will have a quick picture also from the Lander Control Center in Cologne, and the people there, they seem to be quite relaxed, not too much euphoria, probably because they know this is not quite yet the end. There is still some hurdles to go, but Kuhn Gertz, just tell me about everything fine from your side so far?
Everything fine. We, of course, with separation just lost contact with the lander, but this is expected. We're very excited that this step has succeeded so successfully. The big thing for us will be to re-establish the link with the lander in 2 hours, as Stefan said, to check that everything worked okay, that the landing gear deployed, and that we're ready for landing on the Comet.
Okay, Kuhn, thank you very much. Keep on going. We'll catch up with you again. In the meantime, we also quickly check with the control center song in Toulouse. There we are, and Jean-Bernard Dubois, the head of Space Exploration Mission Operations, is hopefully there as well. Jean-Bernard, any reactions from Toulouse?
Yes, in Toulouse, everybody is very happy, as you can see here. We have received this very good news, and what we can say now is that it's like a birthday for Philae.
Okay, Jean-Bernard, thank you very much. And yeah, let's keep our fingers crossed for the next big section in a few hours from now. Thanks for now. And before we go into a short break before lunchtime, I'm back here again with Mark McCaughrean, of course, the Senior Advisor to European Space Agency's Science and Robotic. And I said this now by heart. I hope it's correct.
Maybe, yes. We'll talk later.
Sort of. But before we go, just a quick look again, because I'm sure we received many more tweets, and we would like to just pick one or two if we can see them, so that Mark can comment, because obviously people would be much more interested in hearing your comments than mine on those tweets.
Well, let me say one thing while we're waiting here. You know, what's amazing about what we've just done is we've given up the careful control we've had over this spacecraft for years and years and years. It's all down to Isaac Newton now. It's down to the laws of physics. We're on the way to the surface. We're off the spacecraft, but you know, that's where the tension really begins. So if Isaac's friendly to us, we'll have a great landing later on today.
All right, you trust in Isaac Newton, I hope. Let's hope. If we've got some of the tweets, let's just pick a couple. Happy scientists, yep,
absolutely,
one is standing right next to me. Really hope everyone teaching physics today will be talking about it.
I've had some emails from some of my friends who are professors back in the UK, and they're all following this, so and hopefully they're talking to their students today, absolutely.
And I like this one as well, Astro Katie, whatever happens with Philae, Rosetta mission has been fantastically successful. We've tasted comet dust, heard it sing.
Well, thank you, Katie. Always good to see you online, and thanks very much to everybody who's really helping promote the mission today.
Okay, well, that's some beautiful reactions there. Mark,
absolutely.
If you just turn to the camera, because we would just like to pick up your reaction on what's happened so far.
You know, there's lots of congratulations, but this is one step out of many today. It's great. Because we're now off the spacecraft, and as I say, it's down to Isaac Newton, and this crazy comet's going to tell... It's now our life, because it's the gravity of the comet, it's the winds from the comet that are going to define what happens next in a way. I mean, we have to establish where we were, to establish where we're going to be. There's lots of work to be done in the next 7 hours. But, you know, I don't have any fingernails, so I won't be biting them. They're gone already at this point.
Okay. Mark McLaughlin, thank you very much. Take a short break. We will take a short break now. However, if you would like to keep an eye on the main control room, you can continue to do so, because the cameras will stay in there and you will be able to watch as things unfold. We'll be back again with our live coverage here from the European Space Agency at 12 o'clock noon, and around that time we expect the signal from Philae that it's well on its way to the comet. So do stay tuned, and I hope to see you soon.